Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 2 of a unit attempts. Let's begin with today's class. In today's class we are going to discuss Bohr's model. This is basically a part 02 of a Bohr's model. If you remember the previous class, we have designed Bohr's model for the hydrogen atom, as well as we have derived the relations, and let's look at those relations. That radius of an electron that is orbiting around the hydrogen atom, but we have derived it with respect to z. That means if it is for any atom, I could have a relation, and that relation of radius could be given as r directly proportional to the n square by z. If I replace it with the r0, then r0 was the 0.53 Armstrong. Armstrong stands to 10 to the power minus of 10 meter. Velocity, or relation of velocity, would be equals to v directly proportional to the z by n, where if I remove this proportionality constant, it's a c divided by 137, and from this it's 2.2 into 10 to the power 6 meter per second. Next, we have derived the time period. This time period was t directly proportional to the n cube by z square, and this t naught was 1.51 into 10 to the power minus of 16 seconds. Next, it was the frequency, and the frequency was f directly proportional to the z square divided by n cube, or I should say it's an f naught that is equals to 1 by t naught. And last but not the least, it's an energy which is equals to minus of 13.6 multiplied by z square by n square. When I have used the z as an atomic number, z is the atomic number, while n is the principal quantum number. We have derived and used this many we have derived and this use this many terms and quantities for the hydrogen atom. Now let's look at the ionization energy, excitation energy, and the binding energy. So let's begin with the ionization energy and the potential energy. So what ionization energy is? It is the minimum energy required to ionize an atom, that we call as an ionization energy. It is the energy required to make the electron jump from the present orbit to an infinite orbit. So if you want to jump your electron, if you want that your electron should jump from the present orbit to an infinite orbit, and as you understand that at an infinite the energy is zero, so it would be equals to E infinite minus of E at that orbit. This is equals to 0 minus of 13.6 z square by n square. So this could be E ionization could be given as plus 13.6 multiplied by z square by n square. This is the ionization orbit. Now let's look at this for H atom, for hydrogen atom in the ground state. As we said, hydrogen atom, that means Z is equals to 1, and next it's a ground state, that means N equals to 1. So E ionization could be given as it's a 13.6 multiplied by 1 square by 1 square, it's a 13.6 eV. Now let's define the ionization potential. It is the it is the potential difference through which an electron needs to be accelerated, so that it acquires energy which is equals to the ionization energy. That is what we call as an ionization potential. So ionization potential could be given as ionization energy divided by E. So this is ionization potential. Now let's look at the second. It's an excitation energy and excitation potential. So what is excitation energy? Let's have a look. It says that when an electron is given energy from external source, it jumps to an higher energy level, and this phenomenon is known as the excitation. And what is excitation energy and potential? It is the minimum energy required to excite an atom is called as the excitation energy of the particular excited state, and corresponding potential is known as the excitation potential. So excitation energy could be given as, that is the energy in the final state minus energy in the initial state. And excitation potential excitation potential would be equals to an excitation energy divide by E. I hope this is clear. Let's look at the binding energy, what it is. The binding energy of a system is defined as the energy released when its constituents are brought from infinity to form the system. This is the binding energy. So we can understand that if an electron and a proton are initially at rest and brought from large distances to form an hydrogen atom, a 13.6 eV energy will be released. So binding energy of the hydrogen atom at at ground state is 13.6 eV. I hope this is clear. Is it clear? Now, do you have any doubts up till now? Is there anything? Do you have any doubts? Is there anything? No? Great. So, ready for the questions? Let's have a look. The question says that find out ionization energy of of electron orbiting around lithium in its second stable orbit. So how will you do it? How will you do it? What is ionization energy? It was E is equals to, this is the total energy minus of 13.6. It's a Z square by N square. But ionization energy, that is equals to energy at the infinite minus of energy at that particular location. So energy at infinite is considered as a zero. This is minus of 13.6 multiplied by Z square by N square. This will be the situation. So what I need to do is, it's an E is equals to this minus minus plus 13.6 multiplied by Z square by N square, and this will be the plus 13.6 multiplied by Z. They have given me the lithium, it's Z equals to 3, so it's a 3 square, divide by, it is orbiting in the second stable orbit, so it's a n equals to 2, this is equals to 4, so this is 13.6 by 4 multiplied by 9. This would be the answer, certain electron volts. This would be the answer. I hope this is clear. Is it clear? Are you sure? Ready for one more question? Ready for one more? Great. Let's have a look. The question says that find out excitation energy required to move an electron from second stable orbits to third excited orbit for hydrogen atom. How will you do this? So basically this is an energy required we need to find out for this from the second stable orbit. It is initially at this to the third excited orbit. So this E excitation required would be equals to energy in the final orbit minus energy in the initial orbit. When I say it's an energy in the final orbits, when I say it's an energy in the final orbits, what we understood is that it is the energy in the third orbit minus energy in the, it's a, sorry, it's a third excited, so this should be energy in the fourth orbit. So energy in the fourth orbit minus of energy in the second orbit. So this is equals to this E required would be equals to E4. It's a minus of 13.6 by n square because this is for hydrogen atom. Minus of minus of this is, let's call this n equals to 4. This is n2 and n1 equals to 2. This is n2 square minus of 13.6 by n1 square. So this is equals to minus of 13.6 divided by n2 is 4. This is divided by 16 minus minus plus. This is equals to 13.6 divide by this is equals to 4. So if I solve this, it should look like this delta E. It's an excitation energy that would be, it's a plus 13.6 divided by 4 minus 13.6 divided by 16. So if I do this, it's a minus of 13.6 by 4. What it would be? 13.6 divided by 4, it's a 3.4 minus of 13.6 divided by 16. This will give me a 0.85. So if I solve this, it's a 3.4 minus 0.85, that it would be 2.55 EV. So this amount of energy should be, given from the external source, so that this electron can jump from the second stable orbit to third excited orbit. I hope this is clear. Now, let's suppose if I have been asked excitation potential 2, then what would be the answer? So excitation potential would be equals to 2.55 EV divided by E. So basically this is 2.55 EV. That means it's a 1.6 into 10 to the power minus of 19 joule divided by E. It's a charge of an electron which is equals to 1.6 into 10 to the power minus of 19. This has gone, this has gone. So this excitation potential, it's a V excitation, then it would be equals to 2.55 joule. That's it. You got it right. Correct. I hope this is clear. Is it clear? This is clear. Do you understand this? Have you? Have you noted it? Are you sure? Great. Now one more thing. What I want the relation between potential energy, kinetic energy, total energy and binding energy. Let's have a look. It is the relation of, or relation between, potential energy, kinetic energy, total energy and binding energy. So let's have a look the relations between the different energies. So when I say it's a kinetic energy, then the kinetic energy of this, it's an E square divided by 8 pi epsilon naught into R. If I say potential energy, then this will be equals to minus of E square upon 4 pi epsilon naught into R. If I say total energy, then it is the addition of potential energy plus kinetic energy, and that would be equals to minus of E square divided by 8 pi epsilon naught into r. Now here we are not going in the how this has arrived, and because you have seen it in the last lecture, but we want to derive a relation between this three, and that what would be the situation. Let's observe this very carefully. This is kinetic energy, this is total energy, both are same in value. I'm talking about the value, but kinetic energy would be always positive and total energy would be always negative. So what I can write is that kinetic energy is equals to mode of the total energy. That means if total energy is considered in a mode, then kinetic energy and total energy would be equal. First thing. A second thing, let's have a relation between kinetic energy and potential energy. Look at this. This is e square by 8 pi epsilon naught r, while this is minus of e square upon 4 pi epsilon naught r. That means I can write like this, that potential energy, or I should say mode of potential energy, is equals to 2 of the kinetic energy. Its mode of potential energy is equals to twice of the kinetic energy. Is it clear? Is it clear up till now? Is it clear? Are you sure? Are you sure? Can you do this? Great. So mode of potential energy is equals to twice of kinetic energy, and if you have written this, it's a mode of potential energy is equals to twice of kinetic energy. What about the binding energy? What about it? So when I write binding energy, when I write a binding energy, then I could say that this binding energy would be equals to negative of total energy. So binding energy would be always it is a negative of total energy. One more thing. What total energy in negative represents? What does it represents? That's negative in total energy represents that electron is attached with central body. Yes, it represents that it is being attached, it has been attached with the central body. That means here a central body is the atom. If this has been provided a certain amount of energy, if this has been provided a certain amount of energy such that this is zero, then it will leave that orbit and move to an infinite. It's a binding energy. I hope this is clear. Is it clear? Is it? Are you sure? So ready for one of the question based on this concepts. Let's have a look. Let's suppose they have said that an electron orbiting around helium in first excited state, find out its potential energy, kinetic energy, total energy, binding energy. So first let's find out the total energy, because I know the formula directly. It's a minus of 13.6 multiplied by z square by n square. Now they are talking about the helium, that means z equals to 2. They are talking about the first excited state, so they want that n equals to 2. So from this I could have its a total energy is equals to minus of 13.6 multiplied by z square, it's a 4, n square, it's a 4. So this is minus of 13.6 ev. This is the total energy. So I have done this. Next it's a time for the kinetic energy. I must understand that kinetic energy is equals to mode of the total energy. So this is equals to plus 13.6 ev. I did this. I understand that potential energy would be twice of kinetic energy but in negative. So it is twice of kinetic energy, but it is in negative. It's a minus of 2 multiplied by 13.6, which is equals to, it's a 27, or I should say minus of 27.2 ev. This is potential energy. I hope this is clear. This potential energy is equals to minus 27.2 ev. And what left? Yes, it's a binding energy. So binding energy is equals to negative of total energy, and I received the total energy as minus of 13.6. So this is minus of 13.6. This should be equals to plus 13.6 ev. This is the binding energy. That's it. You did it everything. I hope this is clear. So basically this is the magic of this relations. Basically these are the interrelations that helps a lot, that you need to identify any one of the energy, and from that you can calculate an energy, any of the energy. I hope this is clear. Even same is the relations in the gravitations as well. When in that, if you remember that in the gravitation we used to calculate the energies of the artificial satellites, or we can say even the energies of the planets. So even at that time a same relation can work effectively. In those situation, artificial an artificial satellite will behave as an electron, and let's suppose if it is an artificial satellite, then our earth, which is a central body for that satellite, will behave as the atom, as it is an atom who behaves as a central body in this case. So do you understand this completely? Are you sure? Do you have any doubts? Is there anything? Is there anything? Any doubts up till now? Do you? Great. So now let's look at the very next applications, but very very effective applications. Let's suppose if I need to find out number of spectral lines obtained due to the transition of electron from nth orbit to lower orbits. It is something like this, that let's suppose this is the n equals to 3 and this is the n equals to 1. When I say n equals to 1, it's a ground state. Yes. So when an electron jumps from this orbit to this orbit, it is going to emit certain number of orbits. So this is what I have obtained. It's, let's say this is from nth orbit to the ground orbit, to the ground state. So number of spectral lines emitted would be equals to n minus 1 divided by 2. Please keep this in mind. This relation can help me to get the number of emitted spectral lines when electron jumps from the nth state to the ground state. Does it clear up till now? Is it? Great. So let's look at this. This is the energy is in the ev, and this is the ground state, n is equals to 1. So I have mentioned the energy states. This is the first energy states, which would be minus of 13.6 by n square. Definitely this diagram is for the hydrogen atom. So for hydrogen atom I have taken by default z equals to 1. So this is total is equals to minus of 13.6 by n square, and when n equals to 1, this is equals to minus of 13.6. When I switch to the second energy state, it's an n equals to 2. So this is equals to minus of 13.6 by 2 square. It's a minus of 13.6 by 4. Basically, it's a minus of 3.4. It's a third state. So this is minus of 13.6 by 9, which is equals to minus of 1.51. Next, it's an n equals to 4. It's a 0.85 and onwards. If I switch to the infinite state, it would be a 0. So this is the energy level diagram, as well as I request you guys to please remember this. We must know this. We must know this. We are going to use it. Now let's look at this. Even this is very informative diagram, that when you jump from the any of the state to the ground state, that is, in this situation you have jumped from the infinite to the ground. In this state you have jumped from this state to and this state. In this state you have jumped from the third energy state to the ground state. In this you have jumped from the second energy state to the ground state. This will give us the ultraviolet region of spectra. I hope this is clear. Next, when you jump from the any of the state to the second orbit to the n equals to 2, it will give us the visible spectrum. If you jump from the any of the state to the third state, it will give me the infrared spectra. I hope this is clear. Is it clear? Is it clear? Are you sure? Did you got this what I want to say? Have you? Great. So in hydrogen atom, excitation energy to excite an electron from ground state to first excited state will be. So when I say it's a ground state, it's an E initial minus of 13.6. Already mentioned hydrogen. Yes. To the first excited state, it's an n equals to 2. It's a minus of 13.6 by 4. It's a minus of 3.4. That is equals to. So where to excite? From the ground state to the first excited state, that will be equals to minus of 3.4 minus minus plus 13.6. So this will be equals to plus 10.2 ev. And from ground state to second excited state, the second excited state, it's an, let's call it, it's a EF dash, it's a minus of 13.6 by 9. It's a minus of 1.51 ev. So it's a minus of 1.5 plus 13.6. This is 12.9 ev that we have already calculated for some different values. And in hydrogen atom, when electron makes a transition from an excited state to the ground state, when an in hydrogen atom, when an electron makes a transition from an excited state to the ground state, so basically it has been at here and it is going to move towards this from the ground state. This is, let's call this E1, this is an E2, and E2 is greater than E1. Then its kinetic energy increases while potential energy and total energy decreases. Please keep this in mind. I hope this is clear. Is it clear? Is it clear? Are you sure? Now, do you have any doubts up till now? Is there anything? Is there anything? Are you sure? Are you sure? Great. Let's have a look at certain quick questions. The question says the minimum energy required to ionize an atom is known as the potential energy, binding energy, excitation energy, ionization energy. Yes, this is correct answer. It is the minimum energy required to ionize an atom. That is what we call as an ionization energy. Next, the minimum energy required to excite an electron of an atom. To excite an electron of an atom is known as the excitation energy of the particular excited state. Next, it's an energy of a system. Energy of a system is defined as the energy released when its constituents are brought from the infinity to form the system. Yes, it's an binding energy. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Do you understand this completely? Have you? Have you understood this completely? Are you sure? Do you? Great. So now, are you ready for one of the question? Let's have a look. Let's suppose the situation is if if excitation energy is plus 3.4 ev, if excitation energy is, sorry, it's a plus 10.2 ev, and atom was at ground state. So the question is find out number of spectral lines emitted. Find out number of spectral lines emitted if this electron jumps back to the ground state. How will you do this? What is to be done? What do you think? How can I do this? So, so what they have said is that excitation energy is plus 10.2 eV. So first thing is, what is excitation energy? That you are at ground state and you have been provided a certain energy so that you can switch from this ground state to this upper level. It is the excitation energy, but they have provided me the excitation energy of plus 10.2 eV. So from where to where I should switch? How could I find it out? So if I remember the diagram of an energy diagram, then you must remember that this was minus of 13.6 if it was n equals to 1. For n equals to 2, it is equals to minus of 3.4. Yes, this is n equals to 2. So if you jump from this to this, minus of 13.6 to 3.4, it is the difference. The difference between this two, it's a 10.2 EV. If you remember this, it's very good. If you don't remember it, let's have a look. We understand that delta E is equals to E final minus of E initial. What is E final that we don't know? It's a minus of 13.6 by n square. This is minus minus plus. It's a 13.6 because here I have put n equals to 1 whole square, and this is equals to 10.2 EV. So from this it's an E final is equals to 10.2 minus of 13.6. So this is equals to minus of 3.4, which is equals to minus of 13.6 by n square. So this 2 has gone, and n square would be equals to plus 13.6 divided by 3.4, which is equals to 4. This is equals to n square. From this it is clear that n equals to 2. That means your electron was in the ground state. It has been provided a certain sort of energy of 10.2 eV, and it has jumped to this level. Here it was n equals to 1, here it was n equals to 2. It feels unstable over here, so it has jumped back to the ground state, and I need to find out a number of spectral lines. This was the question. Go through it one more time. So it says that find out number of spectral lines emitted. Find out number of spectral lines emitted if this electron jumps back to the ground state. If it jumps back to the ground state, you need to find out the number of spectral lines emitted. So it was at n equals to 2, and if it jumps at 1, what would be the number of spectral lines? It's an n is equals to n into n minus 1 divided by 2, where n would be 2. It's a 2 into 1 divided by 2. This is equals to 1. That's it. So one spectral line will emit it, and that spectral line would that energy would be 10.2 eV. Yes, basically it is a difference of the energies at higher state to the lower state. I hope this is clear. Is it clear? It is clear. Are you sure? One more question. One more. Let's have a look. They will ask me that find out angular momentum. Find out angular momentum of an electron of an electron in Bohr's hydrogen atom in Bohr's hydrogen atom having having energy of minus of 3.4 electron volt. How will you do this? What do you need to find out? You need to find out angular momentum. Angular momentum L would be equals to n into h by 2 pi. So what you need to do, you need to find out the angular momentum whose principal quantum number is n, and in that energy state its energy is minus of 13 or minus of 3.4, sorry. So as now I must remember that minus of 3.4 can be achieved by minus of 13.6 by 4, and this is the case of n equals to 2. But if you don't remember this, let's say if you don't remember this, then what you need to do is compare this with minus of 13.6 by n square, and you will get an answer n equals to 2. So from this that's L equals to 2 into h by 2 pi. This 2 has been gone, and this is equals to h by pi. This is the angular momentum of an electron orbiting around the hydrogen atom in the second stable orbit. Is it clear? Is it clear? This is the L equals to h by pi, where h, what is h? What is it? What is it? H. Yes, it's a constant. Which constants? It's a de Broglie's constant. Correct. Now let's look at the certain limitations of Bohr's theory. When I say it's a Bohr's theory, we can say that it is valid only for one electron atom. That means let's say H or He plus or Li plus 2 or Be plus 3, etc. This is valid only for one electron atom. Next, orbits were taken circular, but according to the Sommerfeld, these orbits are elliptical, as this is the case of the planets too, that we have taken and we have derived everything as we were considering that this all orbits will be the circular, but according to the certain researches, they say that these orbits are not circular but they are elliptical. Next, intensity of the spectral lines could not be explained. We don't know how this has arrived. A nucleus was taken as a stationary, but but we know that a nucleus also rotates on its own axis. We don't know how to deal with that. It could not explain the minute structure in the spectral lines. Next, it did not explain a Zeeman effect. A Zeeman effect is it's a splitting of spectral lines in magnetic field, and it cannot even explain the Stark effect. The Stark effect is it's a splitting of spectral lines in electric fields. It did not explain the doublets in the spectrum of some of the atoms, like sodium is having the doublets. It can have the spectrum of 5890 Armstrong, as well as it can have the spectrum of 5896 Armstrong. So it cannot explain all this. So there are certain limitations. There are certain limitations of Bohr's model too. Let's look at certain quick questions. The question says, which of the following is a limitation of Bohr's atomic theory? Intensity of spectrum lines could not be explained. Yes, correct. It is valid only for one electron atom. Yes. Orbits were taken circular. Yes. So all of the above is the correct answer, because everything above is correct. Next, Bohr's atomic theory. Bohr's atomic theory could not explain the blank effect. It's a Zeeman effect and Stark effect. Yes, correct. Absolutely correct. So this both A and B is correct, that Bohr's atomic theory could not explain this both the theories. I hope this is clear. Is it clear? Is it? Are you sure? Great. So let's wind up this session over here. This was the Bohr's atomic model. here we have completed the Bohr's atomic model for the hydrogen atom. I request you guys to please go with this relations. Have as many questions as possible because these are the units. This modern physics is having an capability to produce a very good amount of questions in the competitive examinations. There are certain chances that we may ignore it because this is the last sections of the class 12 physics, but these are the region which I understand and which I feel that this is the section which we call as in modern physics is having maximum probability of a questions. If you observe the previous year asked questions very carefully, differentiate it into the different segments, that electrostates, current, electricity, magnetism, and modern physics, and all that, you will find that maximum number of questions belongs to the category of modern physics. So please do not take this lightly. This is very essential. And atom and nuclei, even the next unit, this will help you in chemistry questions too. So this is a win and win situation. Please do it. Please do it. Do not ignore it. Thank you. Have a good day. Take care. Bye bye.